Welcome to module 19 of database management systems. We have been discussing relational database design, and this is the fourth module in that series. In the last module, we have discussed about algorithms for functional dependencies, lossless join decomposition and dependency preservation. So, based on these foundational algorithms and concepts, we will in today's module get into understanding the core design aspects of relational databases, that is the normal forms, and how important they are in terms of the relational design. We would specifically learn about decomposition of a relational schema into the third normal form and into Boyce-Codd BCNF form. So, our topics will be the three normal forms, decomposition of 3NF and into BCNF. So, starting with the normal forms. So, normal forms or normalization of a schema is a technique of refinement to organize the data in the database. So, the question naturally arises as to why do we need to do this refinement after we have done a design based on possibly the ER diagram based approach that we had talked of. We had identified the entities and we had identified the attributes for the entities, their relationships. Then why do we need to normalize? The answer to this question lies in the fact that a design for a relational schema may give rise to a variety of anomalies in terms of the data. These are typically three anomalies which concerns us most: the insertion, the update and the deletion anomaly. So, the anomalies happen when there is redundancy in the data in terms of the schema, and whether there will be redundant data and how much and what kind of redundant data would be there depends on the design of the database schema, depends on the design of the normal form that we are using for it. But if we have redundancy, then there is potential for anomalies, and therefore, we want to reduce the redundancy and get rid of this anomaly. So, we will quickly take a look into the anomalies that are that we are talking of. First one is called an update anomaly. So, we are showing you a snapshot of an instance of a database which has three attributes, and you can look at the row having two entries, the last two rows for employee code 519, and there are two different addresses in these two different rows. So, if we know that the employee will have a unique address, or in other words, if employee ID would determine the employee address, functionally determine that employee address, then this situation is not possible. So, but when we try to update, then it is for example, the employee's address has changed, and while making that change, this change will need to be incorporated in all the records having the same ID, and if because of some coding error or something we miss out to update any of the address fields, then we will have a difficulty, and that difficulty is having inconsistent address data as in this case. So, this is known as update anomaly. Similarly, I could have an insertion anomaly which I am illustrating here in terms of another database schema which has four attributes, and we have faculty ID, name, the hiring date and the course name. Naturally, given the faculty ID, the faculty name and hire date should be unique. Now, suppose a new faculty joins, and as soon as the faculty joins, he or she may not have an assigned course. So, if we want to enter that record here, we will not be able to do that, because we do not have any value for the course code. So, either we use a null value or we cannot actually enter this value. This kind of situation is known as a insertion anomaly. Similarly, I could have a deletion anomaly in the same table. We are showing that in the table, the first highlighted row, for faculty ID 389, if that faculty stops taking any course for the time being. So, the association between 389 and the corresponding course code will be removed, and once you remove that, you remove this whole record. In the process, you actually lose the whole of the faculty information, the ID, name and hire date. So, these are difficulties in these relational schemas, and that lead to a whole lot of problems. So, the resolution for this lie in terms of decomposing the schema, that instead of having one relation, I will decompose this set of attributes into multiple different relations. So, for example, the update anomaly can be removed if we have two different tables, one that maintains ID with address and one that maintains ID with skill. So, in that case, what will happen if the for every ID the address will not be repeated. So, if the address is updated, it will be updated only at one place and it will not feature in the other table. Similarly, to avoid insert or delete anomaly, the other table schema can be split into ID, name and hire date as one table and ID and code, course code as another table. And you can easily understand that if this is split in this way, then you cannot have an insert anomaly, because you can insert a new faculty without assigning a course to him, because that will feature in as a separate record in a different table. Similarly, in the same way, the deletion anomaly also disappears. So, these anomalies are resultant of the redundant data that we are having and can be removed by taking care of the process of decomposition. Now, while we decompose, then we would desire certain properties to be held, and we talked about this loosely earlier as well. We would require the lossless join decomposition property, that it should be possible to take any instance of the two or more decomposed relations and join them by natural join using common set of attributes and get back the original instance of the relation. If that does not happen, then the relationship is lossy. We have discussed it at length in the last module. At the same time, we would want that all functional dependencies that hold must be testable in the decomposed set of relations. So, all functional dependencies, when they are projected in terms of the decomposed set of relations, they must be testable within them, so that to test for a dependency, I do not need to carry out a join. This is a point we discussed in the last module as well. So, based on that, once you start with the original schema, you can check for what are the different possibilities or sources of redundancy, define constraints based on that, and step by step you could convert a schema into a one normal form, have more constraints put onto it, convert it into two normal form, have further constraints, decompose it into third normal form, and so on. So, normalization is the process through which we do this kind of decomposition and make sure that once a relational schema is expressed in terms of a normal form, it satisfies a given set of properties that that normal form should adhere to. And the common normal forms are 1NF, 2NF and 3NF. And loosely speaking, when we say if a database schema is normalized, we usually mean that it is in the 3NF form or third normal form, and most third normal form relations are free of insert, delete or update anomalies. So, that they are a good positive in the design. Of course, these are not the only normal forms. As you can see, there is a whole lot of list of variety of normal forms. We will not study all of them, we will study further in the next module the other two highlighted ones. But first, let us get started with the first normal form, which we had talked about earlier as well. That first normal form is one where the multi-valued attributes are not allowed. So, if you think about a relationship where you have a student relationship between student, her name and the courses taken by the student, then since the students take multiple courses, the C name in this case can take multiple values. So, we do not allow that, we expand them into different rows, and that once we have done that, we say the relation is in the one normal form. But one normal form may give rise to a variety of different redundancies and therefore, anomalies. So, this is another instance. In fact, the earlier instances that you saw all of them were also in one normal form, but they had deletion, insertion and update anomaly. So, here is another example where we are illustrating that. So, it is possible that if I have a functional dependency x determining y, which is non-trivial functional dependency over the set of attributes, and x is not a super key, then there exists a redundancy between x and y attribute sets. So, on the left we have shown an instance of this relationship only on the x and y attributes, and you can see since x is not a key, I can have two rows having the value 1 in x, and since the value is 1 in x, the value y will be same for these two rows, and we have redundancy of that. Please remember that x is not a super key. So, there are other attributes which actually form the super key, and therefore, such instances are possible. Whereas, if you look at the right column where the left hand side x is a super key, then such instances will not happen. Moving on, the second normal form which is obviously a relation is in second normal form if it is in first normal form, and it does not have any partial dependency. So, what is a partial dependency? I have given the definition here. Partial dependency, y determining a, if that can hold in the set of functional dependency, then if I have that y is a proper subset of a candidate key and a is a non-prime attribute. A non-prime attribute is one, which one? Non-prime attribute we defined in the last module is an attribute which does not feature in any of the candidate keys. So, if y is a proper subset of a candidate key which functionally determines a non-prime attribute, then this is known as a partial dependency, and if there is partial dependency, then the relationship is not in second normal form. So, second normal form will require that the relation is in 1NF and there is no partial dependency. So, here we are showing an example where on the left you can see that SID and CNAME together forms a key, and SID determines SNAME. So, SID and CNAME together also determines SNAME. Naturally, SID determining SNAME is a partial dependency, because the left hand side SID is a proper subset of the candidate key SID CNAME, and SNAME is not featuring in any candidate key. So, SNAME is actually a non-prime attribute, and the result of that, as you can see in the first two rows or in the third and fourth row, you can see that SNAME is repeated. So, there is redundancy, and therefore, consequently we will have anomalies that we have talked of. But we can normalize, we can decompose this into two separate relations R 1 and R 2, as I am showing on the right, where you associate SID and SNAME in one table and SID and CNAME in other table. Naturally, then the dependency that the partial dependency that you had disappears, because SID determining SNAME in R 1 now is not a partial dependency, because in that table SID becomes a primary key. So, it does not qualify as a partial dependency. So, R 1 and R 2 both are in second normal form, and you will get rid of the redundancy that you saw, and this decomposition is ensures that it has a lossless join. Incidentally, this is we have not guaranteed that it is in second normal form, and it has also the dependency preservation. But it is possible again in second normal form, a relation could be in second normal form, yet it could have some possible redundancy. So, there is a design instance that I am showing with the supplier ID, SID, the status key which are functionally determined by SID, and the product and quantity values. So, that in the table supplier SID and PID together forms a key, whereas and as that happens, you can clearly see that there is a lot of redundancy that you can see in terms of the status happening, and which will cause you different anomalies to occur. So, if I normalize in the second normal form on the right, then I will have a supplier city, say with the three attributes SID, status and city, and another supplier quantity which has SID, PID and quantity. Naturally, in this there is no partial dependency anymore. Earlier we had SID determining status as a partial dependency, because SID is a proper subset of the primary key which is SID CID. But after I normalize, this dependency does not exist, but yet there will be redundancy in this relationship, and the status will continue to be redundant, and for that reason we have to move on to the next type of normal form. So, this I am just explaining here as to what are the possible redundancy, sources of possible redundancy that you can have in 2NF. In the 3NF, third normal form, what you define is your relation first of all has to be in 2NF. So, we are looking at the first definition. There are three forms of definitions given, all of them are actually equivalent. You do not have to worry about why and how they are equivalent, slowly you will start understanding, but we take it in three different forms, because each form of the definition allow us to understand certain aspect of the three normal form. So, the first thing which is true for everything is it has to be in the second normal form, and it should not contain any transitive dependency, which means that I should not, if I have x determining y and y determining z, then I should not have x determining z, which can be inferred transitively, as you know, through the Angstrom axiom. Alternately, there was an alternate definition given later on by Zanillo, and I have stated a simplified version of that at the bottom. So, we will say that a relational schema is in 3NF if for every functional dependency x determining A that holds on this schema, either it is a trivial dependency, which is x is A is a subset of x, or x is a super key. So, this is kind of the condition also, as you had seen earlier, this also is the condition to be in Boyce-Codd normal form. So, you can easily understand that 3NF is a any relation which is in 3NF is also in the Boyce-Codd normal form, but we add a third condition, where we say that we will say this is in 3NF even if the first two conditions are not satisfied, but A is a part of some key. Just note the wording, A is a part of some key, not just the super key. So, if A is a part of some key, then and the first two conditions are also not satisfied, even then we will say that the relation is in third normal form. So, to check for a relation to be in third normal form, we will actually check for whether any one of the three conditions hold. So, this is the definition of transitive dependency, which I have just loosely told you. So, I will skip over this. They have given another example of a very different kind of a relationship, book, genre, author and author nationality. As you can understand, given the book, you know the author, there is a functional dependency, given the author, you know the author nationality, and but author does not actually determine the book, because the author may have written multiple books. But given that book determines author and author determines author nationality, we have that book determines author nationality, and therefore, we have redundancy, possibility of redundancy in here, which is a transitive redundancy due to this transitive dependency that we have. So, here is the earlier example, where you can, as you can see clearly in this diagram. You can, if you note this diagram, you can see that SID determines city and city determines status. So, this is a transitive dependency that SID determines status. So, if that happens, then status becomes redundant, and therefore, there could be anomalies, and we can easily normalize by making them into SID and city and status, and in that naturally that redundancy goes away, because you have no more the transitive dependency in the relationship. You only have SID determining the city, which is a primary key in SC, and city determining status, which is the primary key in the CS. So, there are these are other examples that you can go through, where we have I have taken the example of a student ID, the IID and the department name, and I have shown that what kind of problems you might get into in this. In this case, you can see that the relationship actually is in there, because there are two candidate keys, and so this SID department name is a super key, and this relationship is in the third normal form, because IID determining department name is contained in a candidate key. So, that is the it is in 3NF due to the third condition that we have had shown. So, when you this is where you can there is some redundancy in this schema that you can observe. So, this is just constructed, and you have been, because of this redundancy, you have been able to, we have had to use null values in this case. So, in a third normal form, there is possible redundancy coming in, and these are the different cases that we have to check through. So, next what we so we have seen the different normal forms. First normal form, no multi-valued attribute, then the second normal form, no partial dependency, then the third normal form where you do not have any transitive dependency. So, all these are cascading definitions. So, in third normal form you have no multi-valued attribute, no partial dependency, and no transitive dependency. So, now what we will take a look into is how, if I am given a relational schema and if it is violating any one or more of these conditions, so that the schema is not in the three normal form, third normal form, then how can we decompose it into the third normal form. So, the question naturally is certainly is can it always be done, is the basic question, that can I always decompose a schema into third normal form. The answer is yes, you can, and there is always a lossless join and dependency preserving decomposition into third normal form, which is of great value, because that is, we said, is a desirable properties of our decomposition. If you recall our discussions in the earlier part of the relational design modules, then you would recall that Boyce-Codd normal form also we had discussed at the early stages, and that gives you a decomposition which is lossless join, but it does not guarantee preservation of the dependencies, where third normal form does that. So, naturally there are different algorithms. First, the question is, can you test if a relationship is in third normal form? I will not go into the details of that, and the computer science result here is testing for third normal form is an NP hard problem. So, there is no known polynomial time algorithm for that, but the interesting thing is that actually the decomposition can be done in very simply in polynomial time. So, what do you have? What is the decomposition algorithm? Written in very simple terms. You want to you are given a relation R and a set of functional dependencies that hold on you. So, you first compute a canonical cover. You know what is a canonical cover. So, you compute a canonical cover. So, you eliminate extraneous attributes, eliminate redundant FDs, and you have the canonical cover FC from F. Then you create for every functional dependency x determining y that exists in the canonical cover, you compute, you make a relation, say the ith relation taking union of x and y. So, you call it the relation x y, and you do that for all the functional dependencies in the cover. And after that, if you find that the key does not occur in any one of these decomposed relations as generated, then you generate one separate relation to represent the key. That is a very simple algorithm, and I just wrote it in simple hand, so that you can understand it easily, but here is the formal algorithm. So, if you are interested to rigor, I mean in the rigor of how 3NF decomposition will happen, here is the algorithm, but I will not go through these in steps. So, that ensures that each relation Ri that I have decomposed and generated is actually in third normal form, and this decomposition is dependency preserving and is lossless join. We are not proving that, but we are just using that result. So, here is an example of a schema. So, we have a customer, banker, branch. So, these are the 4 attributes, and these are the different functional dependencies that exist. Now, naturally given this, first thing you will have to do is first thing you have to do is to look at the different look at taking the canonical cover, the minimal cover. So, if you compute try to compute the minimal cover, you will find that branch name actually is extraneous in the first dependency. So, you can remove that and there is nothing else. So, your canonical cover turns out to be this set of dependencies, and then you go over and for each one of them. So, you take each one. The first one is customer ID, employee ID determines type. So, for that you generate a schema customer ID, employee ID and type. Again you take the second functional dependency, employee ID determines branch name. So, you create employee ID and branch name as a different schema, and in this way you will generate 3 decomposed schema in the third normal form. Now, once you have done that, then you find that your if you look into the original key, it was customer ID and employee ID, and you find that here in the third second and the third you already have that. So, you do not need to add a separate relation for accommodating the key, and also the third relation. So, we can now declare that no further key needs to be added, and we have the final 3NF decomposition. So, at the end for the fall detect and delete. So, this is stated in terms of the detailed algorithm, but this is you can say that the employee ID and branch name, the second relation in the decomposition is actually a subset of the third relation. So, you can remove that as well. So, you will be left with only 2 relations in this decomposed schema, which both of which are in third normal form, and this decomposition has guaranteed you lossless join and dependency preservation. So, I have given some practice problems for you. I have also given the solution, but the solution is not in the current run of the presentation. You will see them in the presentation as hidden slides. So, you first try solving them, and once you have solved them, then you look at the solution in the slide. So, there are 2 problems. So, this is the second one, and you can solve them in that way. Next is we will quickly recap on the decomposition of BCNF, Boyce-Codd normal form, which we had seen earlier, and we know that the Boyce-Codd normal form guarantees that there will have be every dependency that exists must be either trivial or the left hand side must be a super key. So, using the algorithms you can test for the Boyce-Codd normal form, which is described here. I am not going through in steps, and here is the more detailed formal algorithm to find determine whether a Boyce-Codd normal form is in a decomposed form is in Boyce-Codd. So, I will just quickly recap on the algorithm to do that. Naturally, for all dependencies you first determine the super key and check if A determining B is a super key or not. If it and that you can easily do using attribute cover. If it is not a super key, then you choose a dependency A determining B which violates, and you form Boyce-Codd goes in every step. It decomposes one relation into 2 separate relations. So, one that you take by taking union of the attributes of A and B, and the other where you take out B minus A, these attributes, these difference attributes you take out from R, and then you add A and make the other relationship. Naturally, in between these 2, A is a common attribute, and since and that will determine A B, because A determines B. So, A will determine A B, that is whole of R 1. So, naturally the lossless join is guaranteed, and you repeat that, keep on doing that for the resultant relations that you have got, keep on decomposing them till you finally close, and you have no more violating dependency, and you will have a decomposition into Boyce-Codd normal form. Here is the formal algorithm again for you to go by steps if you are interested. Otherwise, you know how to do this. Again, I have shown another example here, which is showing that how to decompose in BCNF. So, you should practice these. That is why I have worked them out in steps here. So, here A determines B, B determines C. Naturally, A is the key. R is not in BCNF because B determining C is a functional dependency where B is not a super key. So, you can decompose them in terms of BC as one relation and AB as another relation. Here is another example, a more detailed one of a class relationship which has a whole set of attributes and these functional dependencies, and based on that the candidate key is course ID, section ID, semester and year, and you can proceed with the BCNF decomposition taking the first functional dependency that holds, but the left hand side, the course ID, is not a super key. So, you will replace it by a one relation which is say new course relation and a new class relation which is the remaining attributes, and then you get convinced that course is in BCNF, but the other one, the class, is not, because building and room number determines capacity, where building room number together is not a super key. So, you split it again and you replace class 1 in terms of two new relations, classroom and section, and both of them are in BCNF, and you are done with this. But BCNF, as I am again warning you, BCNF does not preserve dependence. It gives you lossless join, but it does not preserve the dependencies. So, it is not always possible to decompose into BCNF with dependency preservation. So, here is an example which we saw a little earlier, and there are two candidate keys. R is not in BCNF, you can clearly see, and any decomposition will fail JK determining L, and that will require a join. So, this will not preserve the dependencies in terms of the decomposition. Again, I have given a set of practice problems here, which you should try and get confident in terms of the Boyce-Codd normal form normalization. Now, it is always possible to decompose a relation into a set of relation in 3NF if the decomposition is lossless and the dependencies are preserved, whereas in case of BCNF it is not possible. So, here is a table which summarizes the relative comparison between Boyce-Codd and third normal form, because they are the common ones. Boyce-Codd naturally is more strict, it gives you lesser redundancies, but it cannot guarantee that your dependencies will be preserved. So, more often we will accept 3NF as an acceptable normalized decomposition with some redundancy still existing, which is possible, and we cannot get rid of them. So, we have studied about the normal forms and their importance, and how progressively we can increase the constraints to minimize redundancy in the schema, and learn how to decompose a schema into third normal form and also in the Boyce-Codd normal form.